So some of you are saying, hey, how come you haven't been cutting metal here? I expected to see a complete transceiver assembled by this video. But in this particular section, part 3 of the double sideband 10 meter rig, I've been concentrating on the RF power amplifier section. The RF power amplifier wants to make between 1 and 5 watts of CW power, which gives us pretty significant PEP for the double sideband transceiver. And I've had some problems. It's taken a while to get something that I'm happy with, but I'm going to go through the RF power amplifier section. By the next video, we'll have a complete transmitter done, and then we'll work on the receiver. I got some fantastic advice from Bill Mira, who's a longtime DSB, I guess you'd call him, someone that's been through the mill building SSB and double sideband transmitters and receivers and transceivers for some years, and he gave me some good advice. He said, Mike, build a good DSB transmitter, build a good DSB receiver, a direct conversion receiver, and then put them both in the box and switch between them with only the VXO or VFO common between them, and that'll solve a lot of your problems. I have definitely been worried about this sharing of ports on the mixer between the receiver and the transmitter, double terminations, problems with both gain, losses involved with doing that, and I even went as far as to think about doing some switching and maybe putting some analog switches in, some pin diode switches for the RF. It became ridiculous. But he sort of set me straight and said, hey, just build a transmitter, build a receiver, make the VFO common, and then switch between them with the antenna switch. And that, of course, was the answer I was looking for, and it simplified everything.
So people always say, Mike, why are you designing like it's 1980? Why aren't you using normal techniques and parts? Well, remember, we have goals and requirements with the Novice 10. That's driving our component choices. Number one is keep it as cheap as possible. Use commonly available devices. And finally, do a design that's going to result in a PCB layout. You know, one that'll fit in the small box. Okay, I'm going to suspend all of this simple thinking for a minute and pretend that we are systems engineers, RF systems engineers, and we, of course, like nice 50 ohm interfaces, and we have a budget. As we go shopping on Amazon, DigiKey, Mouser, Jameco, RF parts, and so on, we discover that there's a nice ADI synthesizer module. It even has a frequency readout available for 35 or 40 bucks. And we can get hold of double balanced mixers and 50 ohm splitters, filters, amplifiers, and these all have simple SMA interfaces that we can strap together with little jumpers. You know, for under $300, we have at least 80% of what we need already done. That's not bad. Okay, enough of that, but I just wanted to get that out there.
So here it is, part 3, double sideband 10 meter transceiver. Before I get back into developing the various circuits, it's probably time to review how we're going to lay out the chassis that holds the circuit board. This is the time to do that because it's going to dictate exactly how you do your circuitry inside. Are they separate little boards? Is it all on one board? Ugly construction? Boston carvers, you know, with a Dremel tool? What's your method of construction? And that's going to dictate the enclosure that you pick. And it's probably a good time to lay out the components that you've gathered that you think you're going to use. And of course you find out, oh my God, I'm using these huge controls that'll never fit. I better use transistor size controls. Those knobs are way too big. I need to use something smaller, that kind of thinking. In basic terms, we know we have a tuning control. It's a multi-turn potentiometer, so there's a knob devoted to that. Usually that's over here on the left side. I'm just talking about traditional layout for transceivers, QRP rigs and such. The microphone probably is going to go over here to the right. Do we want an onboard speaker? If you want an onboard speaker, think about it now, because you got to know where to put it. Is it going to go on the side? Is it going to go on the top cover? And you better have a jack when you put in the earphones that kills the speaker. The RF output connector, where does that live? Usually it's on this side on the rear, but it might be over here as well. How are you getting power in and out? Are you using a mated set like this? A simple coaxial connection? A grommet with two wires coming out? How are you getting power in? And do you have any ancillary switching? Push buttons, spotting switches, things like that. Are you going to use an indicator? Think about laying out your parts inside the box. Once you've got that figured out, you can probably start hogging metal and mounting parts. The final amplifier stage of the double sideband transceiver is typically a power transistor that requires a heatsink. Whether that's an FET, MOSFET, or it's a bipolar transistor, do you want to take advantage of the aluminum chassis as the heatsink? Or do you have a separate heatsink that lives on the circuit board? These are things to think about early in the design.
So this week I've spent most of my time devoting it to the RF amplifier chain. If you follow some of the designs and projects out there online, you may have seen some of the RF approaches for the 40 and 80 meter DSB transceiver projects. Most of them employ the modern trend of using wideband transformer stages, usually in Class A and in broadband Class AB topologies for the final. And usually there are 3 gain stages following the balanced modulator, developing a few hundred milliwatts to perhaps a couple watts PEP, or maybe 3 watts, 4 watts PEP. For our purposes, I will accept the conversion of CW power to peak envelope power as that 2.66 factor. You know, the 5 watt CB will do 13.3 watts PEP, and so on. And basically when we're talking about packing in a portable station to some remote spot, we want to keep our power budget down, we want to keep our battery size down, and so on. So we want to limit the output power. We also want to limit the output power for practical reasons. Who wants to be transmitting DSB at 1,000 watts or something? So even with our minuscule power, remember that those Class A stages and the Class AB final, and even the relay, all of that current adds up, even when you're not talking. So when you're in the transmit mode not talking, you might have a static drain of between 100 and 200 milliamps. And once you start talking, the current peaks could go up to 400 or 500 milliamps. So that's another reason why we switch power off on receive. Let me say something about cheap parts, available parts, parts that we misuse deliberately on higher frequencies. That's all good. And if you can tame a $1 part and it has enough gain bandwidth to work efficiently in the frequency range you want to handle, then do it. Our little friend, the BD139, which is an audio power and switching device, it's a great example. I've heard that these things have FTs as high as 250 megahertz. Well, let's just say that I think that they're graded out in HFE and in FT, and the stuff we get might not be anywhere near that good. There was an excellent series on YouTube by Charlie, ZL2 Charlie Tango Mike, 5 or 6 years ago, where he made a push-pull parallel amplifier with 4 BD139s. He got 6 watts out, pretty much whatever he did, whatever ferrite he used, whatever bead style or toroid, and this was on 7 megahertz and with 13.8 volts. So don't think you're going to get a lot of power out of the BD139, and especially up here at 28 megahertz, this thing might not work at all. Most people note that lower frequency transistors that they're getting away with on 80 and 40 meters, and even the MOSFETs like the IRF 510, the 520, our little friend, the BS170 and so on. They are great on 80 and 40 meters, but don't think it's going to work so great up on 10. So in order to keep that broadband type design that you like, you may need proper transistors, with FTs more suited to UHF operation if you want to do 10-meter broadband amplifier design. So there are some great examples of newer MOSFETs out there. You can do the broadband approach, but just be prepared, you might need better devices. So I decided to give up on broadband completely, and I decided just to take a look at what they used to do for CBs. Since CB radios are a similar power situation, a similar frequency range, and many of them do single sideband. So let's look at a CB. When you look at the typical schematic, we see this conventional narrowband power amplifier chain. This is the old days where you just designed for one band and you got the best performance you could in that one band. So I see a couple of Class A gain stages. These are LC matched single-ended driver and final setups. The circuit, as you see it, has been unchanged for basically 40 years. The transistor numbers change, the PET devices change and evolve, but basically you've got that 2SC 2078 style final. That device has a gain of between 10 and 15 dB at 27 megahertz and a guaranteed output power of 4 watts with a couple hundred milliwatts of drive. And it has a modest output capacitance of around 50 or 60 picofarads when it's loaded. So normally this capacitance can be absorbed into the matching network or your low-pass filter sections. I'm not going to go into the impedance matching. There's lots online, lots of great YouTubes on doing impedance matching, lots of tools online for doing a simple L match, a T match, a pi match. Basically, we're just taking a few ohms of the device back up to 50 ohms. Now, the old formula still works great. VCC minus VSAT squared over 2 times your desired power output. So that's going to give you something between, probably 8 and 14 ohms. It's a modest low impedance that you need to transform up to 50 ohms.
Hey, I'm willing to try anything. Now, I had done a match off the collector of the transistor with a series L and a shunt C trimmer, and I was getting about 2.5, 3 watts out of the device. So let's just play dumb and use a broadband match using type 61 material. I didn't want to use these small toroids. I had a good size piece of number 61. By the way, the reason we're using 61 is this is getting close to 30 megahertz, and the transition in efficiency between type 43 material and type 61 material, especially with power amplifiers, occurs in this region. So I'm going over to the 61, which has a lower mu. So this is a straight 1 to 4 bifilar wound transformer. It's got 7 turns, a pretty heavy number 22 wire. I maintain the original choke, which is about 1 microhenry, with a resistor across it to DQ it of about 500 ohms. So you can do both with this. You can run the DC right through the toroid. You just have to use a blocking capacitor and appropriate bypassing. So there's really no need for a choke if you use the bifilar wound transformer properly. But hey, I just took my matching network out and I put the 1 to 4 ratio transformer in. So let's see what we can get out of this thing. Look over here at the power meter. And I'm going to really hit it hard just to see what the maximum power output is. Again, we're biased at about 100 milliamps on the transistor class AB. Wow, 3.5 watts right out of the box. I haven't even done anything. There's no filtering, there's no nothing. It's just going through that transformer, and it's already doing better than I did with my L match. And it's not looking too bad on the scope either. once you run that through the pi filter, that's going to look beautiful. So I think I just learned a lesson that if we do have a proper RF transistor, like the 2SB 2078, that's what I've got in here, and an appropriate transformer that can take the power, this is a way to get you from, 10 or 15 ohms all the way up to 50 ohms with a darn good match without really doing any work at all.
I just thought, I haven't shown you guys the schematic yet. Before all of you completely check out of the video, I should at least show the schematic. And you can see we have 3 stages, and I've got a lot of parts on here. But remember, I'm putting all of these parts on this circuit because I know I'm going to a circuit board. And if I don't use some of these parts, I can just, don't populate the holes or whatever. As you can see, it's a narrowband type construction. It only goes broadband just where we put that 1-to-4 transformer at the output of the 2078. So before I go on, this is what it looks like. It's still just 3 transistors. It's just we have a lot of work to get the kind of gain we need up here on 10 meters. So I decided to skip all of the LC matching on the driver and go with tuned circuit stages. Now, tuned circuits are cool because they actually absorb the internal capacitances of the device into the tuned circuit. They tune it out. So that means that some of these devices that might be marginal in wideband circuits can work pretty well on 10 meters if you use an old-fashioned tuned circuit. So for instance, I was able to make the BD139 operate on 10 meters as a driver by using this tuned circuit trick. I still think that better transistors are out there for this, however. Perhaps the old 2N3866 or the CB driver, the 2SC2314, would be better choices. And I wink completely at the base matches. I know these are very, very low, only a few ohms, so I simply put 3-turn links off my tuned circuits and went straight into the bases of the driver in the final. And you know what? It worked fine. You can mimic the CB matching scheme with all those LCs and fool with the parts for days and days, but I just wanted to get there quickly, so I used link coupling. The Class AB bias is the simple diode in the conventional hookup to ground, working against the base emitter junction of the final. And I put a 100 ohm potentiometer across the diode, and I could set the resting current, between 90 and 140 milliamps. I think I settled on 100 milliamps resting current for Class AB. Of course, you have to watch for thermal runaway, and if that happens, it's going to smoke that final transistor. The best practice is to marry the diode to the output device's heatsink as close as possible. I did this by soldering the cathode of the diode directly to the copper heatsink, and my friends, that's very intimate.
So using simple diode biasing on the final stage into Class AB, you're seeing a resting current of 158 milliamps, but actually about 50 of that is going to the driver and the other stages. So it's about 100 milliamps through that final stage. It's fairly stable. Seems to stabilize around 160, and I can set it with this potentiometer. So when I apply drive, I'm finding I have a gain of about 34 dB in 3 transistors. Now that might be a little bit light for us. I might have to put one more stage in, but for 3 transistors that's not bad. And I'm using the BD139 as the driver, and it's a little bit weak at this frequency. I think if we had a real driver transistor, like a CB driver type transistor, or one of the RF TO5s, TO39s that 5179, whatever, you'd find you'd have more gain. But I wanted to use the BD139. It seems very, very happy up to about the 2.5 watt output level. It's a solid 2.5 watts out at 28.5 megahertz. This is a narrow band amplifier design. It's not a wideband design. There's two trimmers and 1 trimmer in the output. So each stage is tuned, which means it's not a wideband amplifier. And I did that to mimic what you'd have in a normal CB, a narrowband amplifier just for the frequencies we're interested in, which is the 10 meter band. Okay, here we are sitting at just about 1.5 watts out. As you can see, the current has gone up, and if you look at the scope, you can see that we have a nice sine wave coming out, even though there's no filtering at all other than the matching structure on the output, which is just an L match. This over here is the collector choke. The collector choke for the final is fairly heavy duty. I found that a smaller core like a 20 or a 37 were heating up, so I'm using a full FT50 core, red to yellow, in the 10 meter band. You can go either way. Just make sure the core is not getting saturated. So let me hit it with a little bit more drive. We'll see what we can get out of this thing. Okay, now the current has gone up to 500 milliamps, and we're about 2.75 watts out. Anyway, that's about all I could do with a 2SB 2078. Is a common CB output transistor. Now it's important that you don't get thermal runaway with this thing. Things are going to get hot right now. You know, with 12 volts and half an amp, that's 6 watts of dissipation going somewhere across this whole board. Not all of it's in the final, of course. Things are heating up. And this thing could go into thermal runaway if your biasing circuit is not stable and tracking the final transistor. I've actually mounted the diode right to the heatsink. I soldered it to the copper heatsink, so the diode heats up with the final. It's pretty much connected thermally. Also, you want to limit your power supply to save your transistor. I would current limit at about 1 amp or maybe 700 milliamps. Okay, it seems happy. Now we're going to remove drive and see what happens to the current. It should settle back again. I'm just going to pull it out of the generator. And there it is. It's come back to 167. We're not in thermal runaway. It seems happy. So that's our Class AB double sideband power amplifier chain. 3 transistors. 2N2222 on the input stage, tuned. BD139 driver, tuned. And 2SC2078 final, tuned. The output of this will go into the 2-stage pi filter. So there's going to be a combination of at least 3 low-pass inductors and 5 low-pass capacitors. This being a narrow-band amplifier, you don't have the harmonic issues that you have with the wide bands. So you don't have to use the ridiculously severe 7-pole, 8-pole type filters on the output. This is a much cleaner situation.
So Mike, my amplifier is oscillating wildly. Well, that's actually a good thing. That means you're doing a lot of things right. Let's remember, we just had some videos on the 1929 Hartley oscillator, and a beat-up tube from 1920 was oscillating with no trouble at all. So you really shouldn't be surprised that a modern transistor with some fantastic gain bandwidth into the VHF-UHF region would not be tempted to oscillate. So I think we can learn something from a Japanese RF production line engineer from the 1970s trying to build a CB. Let's look at his schematic. First, take a look at the bypass capacitor situation. I've put some green circles around them. It looks like a 0.01 microfarad capacitor is a good value for bypassing, at least at 27 or 28 megahertz. A 0.01 looks like 0.6 ohms up here. Notice how the engineer decreases the impedance of his bypass by doubling up the same value, and of course the same capacitor, the same construction, rather than adding different values in parallel. This is a big hint. When you look at a capacitor, we can all agree that it's made up of capacitance, and of course some minor inductors and resistors and smaller capacitances. These parasitics inside the capacitor can get us in trouble. But if you've got a known 0.01 capacitor that you've got a lot of experience with, and you know its characteristics, and you know that all of these parasitic values are well above or below the places where they might be tempted for some kind of series or parallel resonant circuit that might encourage an oscillation, then you're in better shape than if you're using some unknown capacitors. So adding capacitors of the same type is a low-risk technique. Now, if we were to put several capacitors of different construction and values all in parallel, who knows what kind of oscillation opportunity that we could be inadvertently creating. So my message is, don't over bypass. So that means you want the capacitor to work best in your band, not down at ultrasonic frequencies where you get some squagging, or up at UHF frequencies where you can get some crazy parasitic oscillations. You want a capacitor that naturally rolls off the gain of your device above and below your frequency of operation. The same goes for your coupling capacitors. Turns out that 0.01 is plenty high enough at 27 megahertz as a coupling cap. Less may even be called for. 100 picofarads equals 50 ohms on 10 meters. Keep that in the back of your head. 100 puff, 50 ohms. Next, look at all of the dequeuing and swamping resistors. I've got these in red. These lower the tendency for a tuned response that could encourage a component or its stray inductance or capacitance to form a tuned circuit somewhere where you don't expect. The clever Japanese engineer had no time to troubleshoot parasites on his production line. Nothing is free, and all of these things that we're adding to settle down the circuit cause a drop in gain, of course, so the devices need to have excess gain. You might even have to add an extra stage. Look carefully at the low Q matching structures. Most of these bipolar transistors have a fairly low input base to emitter impedance and a low output collector to emitter impedance. They're low impedance devices, especially power amplifier transistors. So you don't want to use high Q tuned circuits, the tuned circuit in the collector and the tuned circuit in the base, basically couple through the capacitance between the collector and the base, forming a TPTG, we used to call it in the old days, oscillator. So the clever engineer has put a 5.6 ohm R310 in the base of the transistor to discourage this type of oscillation. So when you're doing matching sections between stages, especially with power amplifiers, we typically use low Q, Qs of less than 2, and we add those swamping resistors. So I've added one more across the collector of the power amp. You'll see it's right across that radio frequency choke. Typically this resistor will solve a lot of your issues. The value might need to be between 220 ohms and 1500 ohms typically. And since the output impedance of this device, especially if it's at the 2, 3, 4, 5 watt output level, it's going to be between probably 5 and 20 ohms. So adding a little bit of resistance across the plate choke or the collector choke is not going to cause that much loss.